These are measures of model fit. The first one we look at is usually r squared, 0.625. And r squared, according to textbooks, is the proportion of variance explained by the predictors in the model. But I don't know that you could take it quite so literally, right? Because there could be confounders that you didn't include in your model, that they're the ones that are actually explaining some of the variance in the outcome variable. R squared adjusted is also reported here, and that accounts for the number of predictors in the model. So it's a little bit better to use, and a lot of textbooks make a big deal about using it. However, in reality, I've never seen a huge difference, at least for the models that I've worked on, between the two. If you want to report adjusted R squared, that's completely fine. Over on the right side, you see some other measures of model fit. And if you look at the root mean squared error, you can think about that. That's kind of useful. That's kind of like the average residual of the model. AIC and SBC and other information criterion type measures are really useful and important, but they're useful in comparing two models in the same analysis. And so just to use them for a standalone model is problematic. For example, what we could do is we were concerned that cognition was not significant and not contributing and not confounding. We might take it out and see by how much AIC goes up, if at all. And if that's, we can use something to compare two models in the same analysis. Now, an r squared value of 0.625 is relatively high. A lot of the variance in the outcome is explained supposedly by the predictors in the model. But this is context dependent. There's no absolute thresholds for interpreting r squared of the model. Let me explain. In this analysis, our outcome variable is mobility score, but one of our predictor variables is also mobility score, and that tends to explain a lot of the variance. Where you start is often very much related to where you finish in terms of the same measure. If we were doing the same analysis but using a gain score model without the baseline mobility score, which should be omitted from that model, r squared would go down a lot. And when you're trying to predict complex behavioral, physical, social type things, like how someone is functioning at discharge, which also, by the way, is affected very much by the treatment that you receive, predicting the outcome is challenging, and r squared values of 0.15 or so would be considered high. So there are some thresholds in textbooks, but I would really make a determination about r squared based on your data and your model and the environment in which the data were collected and the situations related to how the data were collected. Is very, very much context specific. Okay, we're going to go with this as our final model. If this was going to be a publishable paper, I would certainly take cognition out, put it back in, see what happens to the model. I'd go back and make sure that all of the variables I excluded initially in the first run, maybe some of them might contribute. I might put them into the model and take them out of the model. But this video is already way too long, so let's, in the interest of time, let's proceed and get to our model assumptions, because this is important and it's going to take a while. A lot of the model assumptions and checks that we're going to do are related to the errors in the model. And those errors are essentially us saying that for this person with this strength, this level of cognition, they're these many years old, they're male, we predict their score at discharge would be this, but their actual score was that, and the difference between this and that is the residual, and a lot of our assumption checking is related to residuals. One of the first things we can do is look at the distribution of residuals. In linear regression analysis, the residuals are supposed to be normally distributed. You can have a dependent variable that's not normally distributed, but as long as the errors are relatively normally distributed, then you're still probably okay. Now, every analysis is going to depart from normality in terms of the residual distribution to some degree. How much you're willing to live with, again, depends on your goals and your model, and is very much context specific. Okay? If departures from normality are severe, you can do a lot of other things. You can try quantile regression and try the median or different quantiles. You can transform the dependent variable. You can use a log transformation, a square root transformation, or if the skew is in the other direction, you can reflect it and then use one of those transformations. A lot of different things you can do. And the textbooks will always tell you to transform if there's any problem, or it seems to be they err on the side of transformation. But when you're out there kind of on the front lines doing this work and have to publish the paper, you know that you have to report the results. And once you do these transformations, reporting becomes very much more complicated. Getting the reader to think about the discharge mobility score is very much different than getting the reader to consider the implications of the log or the square root of the discharge mobility score. In any case here, you could do a histogram. I chose a box plot because I don't like the default histogram that R gives you from the OLSR package. But I could probably have altered it and made it a little more granular. There was not enough bins. So what I did here is just gave you the box plot, and you can see, because this is simulated data, this is almost a perfectly symmetrical amount of data above and below the median. And I would imagine the median is very close to the mean. If you have detailed questions about the residual distribution, there's other plots, there's normality plots. You can run descriptive statistics on the residuals. There's a lot of different things, but just at first glance, this looks more than fine. There are some outliers on the top and the bottom. We'll talk about that later. Those may come back for further examination down the road. Another thing in the distribution of residuals, in terms of looking at a quick view of outliers, we're going to look at outliers a little more carefully down the road, is to look at standardized residuals. So what you see here on the left are the raw residuals in a box plot. And on the right, R gives you this kind of data point by data point. And by the way, if you had a really large data set, this is not going to work. But for a data set like this, with 400 and change, I think it's probably fine. The chart on the top right are standardized residuals. So you've taken each residual and standardized them by the standard deviation of the residuals. And what you're looking for here is to look a little more closely at values over 2, but definitely closely scrutinize values over 3 or less than -3. And you can see observation 299 might be something that we come back to look at, or on the top end, it doesn't seem to be too much. You're usually going to have things like this in an analysis. Nothing I see here makes me very nervous, but it's something just to keep in mind when we look further. Usually this would be part of something we look at later, but I'm doing it here because we have the residual plot as well on the left. Now, what did I say at the beginning of this? I said, do not test things before you look at them. I could proceed with the analysis just based on what I'm seeing. This looks, quote, normal enough to me, or Gaussian enough. Do not run tests for normality before you look at the distributions and charts and graphs, descriptives, whatever. Oftentimes these tests come up positive, meaning that there's a significant departure from normality, but it may not matter. You might still be okay. The key is to look at it first and then run the test. So if we look at the test, we see here, R gives you a nice menu of 4 tests. And you can see here from the p-values that only one is significant for departure from the normality assumption. Often more than one of these will be significant, and how much of a departure you're willing to live with is up to you and the context of your analysis. Here, that third test there always seems to come up positive for me, but some of the more common ones, Shapiro-Wilk is the one I usually use. But the other two, in addition to that, are also not significant. Again, here for the p-value, p-values of 0.05 or less indicate there's a significant departure from the normality assumption. So I think we're okay based on the test, but I probably would have been okay just looking at the charts without doing this. But the one thing you shouldn't do is jump right into testing. Some of these tests are sensitive to sample size, right? So no matter how good or how close to Gaussian your distribution is in terms of your residuals, these tests may come up positive if you have thousands of observations. Okay, not all of them. Some of them are more resistant to sample size than the others, but look before you test. I think this is okay. Let's proceed.